Hello everyone. So in this pre-lecture tutorial we're going to continue to discuss how it is that we can actually calculate enthalpies of reaction. If you recall, the last tutorial was about Hess's law, and in that particular tutorial we learned that if we have similar reactions or related reactions to a reaction that's of interest to us, then we can, using mathematical manipulations of the chemical reaction equations, we can actually construct our equation of interest and thereby manipulate the associated enthalpies of those reactions to calculate the enthalpy of reaction for the reaction that's of interest to us. A similar concept is to calculate the enthalpy of reaction using something called the standard enthalpy of formation. And basically what the standard enthalpy of formation is, it's the enthalpy associated with the formation of a compound from its constituent elements. At standard conditions. Okay, where standard conditions would be 1 atmosphere and a temperature of 298 Kelvin. Now, as an example, here we have the standard enthalpy of formation for acetylene. And so acetylene is formed from carbon and hydrogen. And so the associated equation for the standard formation of acetylene would be carbon in its most stable form, which would be graphite, and hydrogen gas as a gas, and we're going to get acetylene out of this. Now, there are a couple of conditions that need to be met in order for a reaction to be considered a standard formation reaction. Again, there are the stipulations on the conditions, but also standard enthalpies of formation are actually reported per 1 mole of substance. And so basically the compound to which the standard chemical reaction equation of formation applies, I must only form 1 mole of it. Okay, so that means if it's necessary for me to actually have fractional coefficients on the reactant side, then that's permissible in this case. In addition, basically the constituent elements that make up the compound must be in their most stable states at standard conditions. And so basically hydrogen is diatomic and a gas at 1 atmosphere and 298 Kelvin. Carbon can exist in several forms. It can be graphite, it can be diamond. And so diamond is a little bit higher in enthalpy because basically it requires elevated pressure and temperature to form it. And so the most stable form of carbon would be graphite. Okay? But essentially what would have to happen is you have the reactants in their most stable forms under standard conditions forming 1 mole of the compound that you are considering. Now, by definition, the standard heat of formation, or the standard enthalpy of formation, which has the following symbol, for elements in their standard state, that would be 0 for each of these. Okay? Now, that becomes important as we then try to apply and use these standard enthalpies of formation. Here's an example of using one. I'm being asked to calculate the enthalpy of reaction for the combustion of acetylene. Now, we're going to break this down in class a little bit further, but if we utilize Hess's law, and if we consider the formation, the standard formation reactions for each of these substances, the acetylene, the oxygen, the carbon dioxide, and the water, basically what we're going to find is we can apply Hess's law to those formation reactions, and if we do, we get a general relationship that essentially applies to all reactions. If I want to calculate the standard enthalpy of a reaction, then what I need to do is sum over the product of the number of moles times the standard enthalpy of formation for all of the products. From that, I'm going to subtract the product of the number of moles, or I should say I'm going to subtract the sum of the number of moles of the standard enthalpies of formation of the reactants. And if I do that, then I'll get the standard enthalpy of reaction. So let's apply this. Okay, for this reaction, if I want the standard enthalpy of reaction, I need to sum up over the number of moles for each product times its associated standard enthalpy of formation. So here's the standard enthalpy of formation of carbon dioxide. So it would be negative 394, and again these units are kilojoules per mole. So this would be negative 394 kilojoules per mole. To this I'm going to add the product of the number of moles, so 2 moles of water in the liquid state, times the standard enthalpy of formation of water in the liquid state. So it would be negative 285 kilojoules per mole. All right, so that completes this term in our general equation. Now I'm going to work on the second term. To this I'm going to, or from this I'm going to subtract the number of moles of acetylene times the standard enthalpy of formation of acetylene, which is plus 227 kilojoules per mole. Now, to that I would add the number of moles of oxygen, so this is 2 moles of the acetylene times acetylene's standard enthalpy of formation, and this would be 5 moles of oxygen. And I would be multiplying the standard enthalpy of formation for oxygen. Notice that it does not appear in the table. And the reason it doesn't appear in the table is because this condition applies. For any substance that is an element under standard conditions, then basically the standard enthalpy of formation by definition is 0. And so this would be times 0 kilojoules per mole, and this portion of the second term would drop out. So all that I have left to do is to actually just do this sum, and from that subtract 2 times positive 227 kilojoules per mole. Notice that the mole units will cancel out. Okay, now if I go ahead and do that math, I end up with negative 2,600 kilojoules. Okay, and again, this standard enthalpy of reaction would apply to this reaction equation under standard conditions, and again, per mole of reaction, if you will, or basically as per this equation that's written and involving each of these stoichiometric coefficients. If I go and allow this reaction to run with 2 moles of acetylene and 5 moles of oxygen to produce 4 moles of carbon dioxide and 2 moles of liquid water, if I allow that reaction to run in that manner, then basically it should actually get a release of 2,600 kilojoules. Okay, so work on the follow-up assignment. We're going to clarify exactly how this particular relationship works in class. Again, if there are any questions, feel free to email or ask questions in class. All right, have a good night.